Example 3. Approximate the instantaneous rate of change of f of x equals 4x squared at x equals 3. Or, we could also ask the question is, find f prime of 3. Those questions mean the same thing. So if we're trying to approximate how much this function is changing at 3, what we need to do is we need to find the average rate of change to the left and the average rate of change to the right of 3. And again, the closer we can get to 3, the better our approximation will be. So instead of getting closer and closer, it makes a lot of sense to start really close. So the way I'm going to set this up is I'm going to create my own table. And I'm going to put 3 in the middle. Now, I need to pick something really, really close to 3 on the left and right, and I want to be the same distance away. So I'm going to pick 2.99 and 3.01. So I'm going to go within 1/100th place of 3. That's generally close enough to get a pretty good approximation of whatever you're looking at. So what I need to do now is I need to find the functional values at each of these points by plugging them each into f of x. So when I plug in a 3 into f of x, 3 squared is 9. 9 times 4 is 36. But then I also need to plug in 2.99 and 3.01. So here, when I plug in these numbers, there's going to be a lot of decimals. So I'm going to be really, really careful. When I plug in 3.01, I get 36.2402. I was expecting something fairly close to 36 because this function is continuous and I didn't change the independent variable by that much, so I wasn't expecting the dependent variable to change all that much either. Similarly, if I plug in 2.99, I get 35.7604. So here, I've made the decision to round to 4 decimal places. Generally, that's safe. You always want to keep at least 3 to avoid rounding error. So now that I have the functional values, I need to do the average rate of change to the left and the average rate of change to the right. So when I do the average rate of change to the left, I'm going to do f of 3 minus f of 2.99 divided by 3 minus 2.99. When I carefully plug those decimals into my calculator and I crunch that number, I get 23.96 for my average rate of change to the left. When I do the average rate of change on the right, I'm going to do f of 3.01 minus f of 3 divided by 3.01 minus 3. When I plug that into my calculator, I get 24.02. So my average rate of change on the right is 24.02. So remember, I'm trying to figure out what this is approaching from the left and the right. Now I could average them. However, I feel fairly comfortable saying that these look like they're approaching 24. And again, this is a best guess, so I'm going to use approximation since I'm not entirely sure yet. But I can say the instantaneous rate of change at 3 is approximately 24. So that's how I set these up when I have a function and I want to approximate the rate of change. Let's look at another. Example 4. The population of a small rural town is given by P of t equals 325 times 1.025 to the t. If time t is measured in years since 2010, approximate the rate at which the population is changing in 2012. So here, I need to first figure out what t I'm actually even looking at. So 2012 is 2 years after 2010, which means that I'm trying to figure out what's happening at time equals 2. I could also write the thing that I'm finding as p prime of 2, so the instantaneous rate of change at 2. We're going to approach this similarly to how we did the last one. So again, we need to set up a table where we're looking around 2. There's going to be a lot of decimals here, so I'm going to give myself a lot of space. So I'm going to go ahead and I'm going to use 1.99 and 2.01. Now, you don't have to go to 100th place. You can try the 10th place or the 1000th place, but you want to be close to 2. You don't want to go something like 0 to 2 and 2 to 4. That's too far away. When we say close, we mean things like 1.9 and 2.1, or 1.99, 2.01, 1.999, 2.001. You get the point here. But the thing is, you do get to pick which numbers you choose, so choose them wisely so you don't have to repeat the calculations. So here, I'm going to take each of these values and I'm going to plug it into my population function here, P of t. So when I plug in a 2, I'm going to get 341 point, now there's a lot of decimals here, so I'm going to write them down carefully, 453,125. 453,125. And again, I'm electing to keep a lot of decimals here because exponential functions are a little temperamental. So the more decimals I can keep, the better. That's how many my calculator reported to me, so I wrote them all down. When I plug in 2.01, I get 340.5374491. And when I plug in 1.99, I get 341.3688217. So we have to be a little careful with decimals. We try not to accidentally type in a wrong one, but hopefully you're able to take these and then use them to find the average rate of change on the left and the average rate of change on the right. So when we do the average rate of change on the left, we're going to do the change in y over the change in x, and we're going to get 8.4303. And when we do this on the right, we're going to get 8.4324. So these numbers are really close, which is really, really good. So here, I'm comfortable saying that the approximate rate at which my function is changing is 8.43. So those are the same in both scenarios. So I've rounded because there's so many. Because they're so close. Now, I want to point out here some of the key wording that was in the problem that told me that I was looking for the instantaneous rate of change. So it says, approximate the rate at which the population is changing. The rate is the instantaneous rate of change. So when you see that word rate, that should send up a signal for you that we're probably finding the derivative, also known as the instantaneous rate of change, at a point. So as you can see, as we move along, there's more and more information that we need to remember on how to interpret these things and apply them. Let's look at one final example here of how we might be able to apply what we know about the instantaneous rate of change to find out further information about a function. Example 5. Suppose we know that for the function below, f of 4 equals 25 and f prime of 4 equals 1.5. Use this information to find the coordinates for points A, B, and C. So here, this one is a little more conceptual. We have to take what we know and see how we can apply it to the situation to try to figure out some stuff that we don't know. So I want you to remember that the derivative, f prime of 4 equals 1.5, is the slope of the tangent line, right? So we know that the slope of this line is 1.5. That's important to us. Now, we also know a point on this line, right? So we know that when x equals 4, y equals 25. That's the point A, right? So we actually already know one of these points. So A is the point 4, 25, right? That's the x, y value. So if we know the slope of a line and we happen to know a point on the line, we can actually use that to get the equation of the line. So remember, the equation of a line is y equals mx plus b. So here we know the slope, which is m, right? So we have y equals 1.5x plus b. And if we want to solve for b, we can use the 1 point we have, because if you have any point on the line, then you're going to know how to solve for b. So we take our point, 4, 25, and we plug it into the appropriate place. So 25 is the y value, 4 is the x value. So 4 times 1.5 is 6, and we subtract 6 from both sides, and that tells us that b equals 19. So that means that the equation of this line is y equals 1.5x plus 19. So if you're not sure why we would want the equation of that line, think about this. In order to find the points b and c, we already know the x value. So that means if we were to take that x value and plug it into the equation of the line, we would get the corresponding y value, which would give us the point we're looking for. Which means that to get that point b, our x value is 4.2. And we're going to take 4.2 and we're going to plug it in for x. So we'll do 1.5 times 4.2 plus 19, and that'll give us 25.3. And that makes sense, right? If you look at the picture, you're expecting the y value to be bigger than the y value at a, because it was above a. And here, if we want to find c, we're going to take 3.9, which is the x value at c, and plug it into the equation of the line here for x. And when we plug in a 3.9, we're going to get 24.85, which again makes sense. We're expecting the dependent value at c to be a little bit lower than the dependent value at a. So by finding the equation of that line, we were able to find the coordinates of all the points on that line for various x values. And we were able to get the equation of the line because we knew the slope of the tangent line through the information that we had about the instantaneous rate of change.